Welcome back. This is the second segment of section 6.1, and I'm gonna maybe just shoot right over to our document camera and discuss some things while moving forward here. So you recall last time we did some interesting things with sine, inverse sine, etc. I talked about the principal root, the alternate root, and how that leads to some unusual kinds of situations that occur from time to time that seem a little bit odd. So one thing that I wanted to point out, and I probably should have said it last time, is that we've talked about how sine functions in this kind of weird environment. What about cosecant? I mean, cosecant should have some similar sorts of properties, right? So if we were to say consider inverse cosecant of the cosecant of 2 pi over 3. Okay, well, cosecant is positive in both quadrant 1 and quadrant 4, just like sine is, and so it should exhibit the same sorts of issues. So if you look at cosecant of 2 pi over 3, that happens to reduce down to 2 root 3 over 3. That's the exact value. And then you ask yourself, okay, so what is the range on cosecant or inverse cosecant? Well, it's either an angle in quadrant 1 or it's an angle in quadrant 4. And the one value that's not allowed is actually the quadrant angle 0. In fact, no quadrant angles are available. So this, because this is positive, well, cosecant is positive in quadrant 1, and so the inverse cosecant of a positive quantity has to be an angle in quadrant 1, which it turns out will be pi over 3. Now notice, these are different. And it's exactly the kind of argument that we made with sine previously, is that, whenever you have some issues with the range and domain, you might have some dissimilarity between the argument that starts and the number that comes out. One thing you have to be cognizant of, though, with cosecant is that there are certain values for which cosecant is not defined at all. And so, for example, if you were to look at a problem like inverse cosecant of 0, and that's an angle, well, we know that cosecant of 0 is undefined. And so the inverse cosecant of an undefined ratio is certainly not a defined angle. This is undefined. Okay, so that was just something that I wanted to mention. Probably, like I said, I probably should have kept it in the previous video, but oh well, here it is. That was already starting to get a little bit long anyways. Okay, so what we'd like to do now is to move on to examples involving cosine. Now, recall that when we did this before, we said that the range on the inverse cosine, maybe I just write that here for posterity. The range on the inverse cosine function is any angle between 0 and pi, inclusive of the endpoints. So it's possible to get 0 to come out of this. It's possible to get pi. But this is angles in quadrant 1 and 2. Now recall, cosine is going to be negative in quadrant 2. So how do we establish the principal and the alternate roots for cosine? So for example, if we had the equation cosine of x equal to say maybe 1/2. If we want to solve this problem, we know that to find x, if we take the inverse cosine of both sides, that will give us one answer. So the inverse cosine of x, x will be the inverse cosine of 1/2. That's one solution. And this is what we would call the principal root. In fact, this is the same for any trig function. It's just whatever the trig function is, the inverse trig of the known value is always the principal root. But what about the alternate root? Well, let's look at what this is. This is an angle in quadrant 1, right? And it has a x value now of 1 and a length of 2. So for some point, R value is 2, right? So here's this angle. This is the inverse cosine of 1/2. But if you were to reflect this down into quadrant 4, it turns out that there is another point whose x value is 1 and R value is 2. And this angle, this quadrant 4 angle, is another solution to this, and that happens to be the alternate root. Now, cosine happens to be really, really easy because the relationship between the sort of principal root and the alternate root is that they just have a difference in signs. So it turns out that you can actually write them both as just plus or minus inverse cosine of 1/2, which turns out to be, what is it for 1/2? That's pi over 3. So in this particular case, we'd have plus or minus pi over 3, right? So a little bit of difference there. And it turns out that the same argument I made for cosecant holds for the situation with cosine and inverse cosine holds for secant as well. You'll have a plus or minus that pops in there. But anyways, let's try to work with these a little bit. I'm going to do another one like this. Maybe look at what happens with some other examples. I won't put as much detail into them, but let's just give this a go. So the first example, how about the arc cosine? Remember, that's inverse cosine of square root of 3 over 2. Now, what this question is asking is, for what angle in either quadrant 1 or 2 is the cosine of that angle equal to the square root of 3 over 2? And we know that that is, in fact, pi over 6. What about another one? How about arc cosine of negative 1/2? Now, there's a tendency to want to say, well, that's just, negative pi over 3, but that's not right, because what this is asking is for what angle in quadrant 1 or 2 is the cosine of that angle equal to negative 1/2? Well, the negative 1/2 gives it away. It's got to be something in quadrant 2, because that's the only quadrant where, that's the quadrant where cosine is negative. And so we have to use this sort of concept as like the reference angle. So the reference angle is this pi over 3, right? Reference angle is pi over 3, but we need an angle in quadrant 2 whose reference angle is pi over 3. And that will in fact be 2 pi over 3, right? How about, how about another one? Pretty simple. How about the inverse cosine of negative 1? Well, there's only one location where cosine is actually equal to negative 1. And that's at pi. Now, it turns out there are special cases where the roots are the same angle. The alternate roots are actually the same angle. Maybe you remember that from college algebra. They talk about what's called the multiplicity of a 0. It's the same kind of concept. There really is only one root for inverse cosine of negative 1, and it happens to be equal to pi, because minus pi is the same angle except for its coterminal. And so you'll have a simplification of the solutions from something like this. So let's see what else we got. These are pretty simple here. We'll get to some harder ones. So section 1, page 5. Okay, so let's try something where we're mixing them up. We've got maybe like inverse of, let's say inverse cosine of the cosine of pi over 3. Well, so when we've got this pairing, it's very, it seems very easy to just like write that number down. And in this case, it actually is true, but I will show you some examples where that does not work so well here in a minute. So let's take, let's just substitute here. We have inverse cosine of, well, cosine of pi over 3, as we've already seen, is 1/2. And we already know this answer because we just did it. It's pi over 3. right? What happens if we put this argument out of the range of the inverse cosine function? Like, let's say, for example, how about the inverse cosine of the cosine of, say, 7 pi over 6? So when we try to simplify this, notice this is going to be the cosine. Cosine of 7 pi over 6 is a negative quantity, and it is in, it has a value of -1/2. No, value of negative root 3 over 2. Sorry about that. So this will become negative root 3 over 2. And now we ask ourselves, what for what angle in either quadrant 1 or quadrant 2 does cosine of that angle equal negative root 3 over 2? And it turns out that this is, in fact, 5 pi over 6. Notice that we went from 7 pi over 6 to 5 pi over 6. And this is the, it would be very trivial to just, write this down as 7 pi over 6, but it's actually a false statement. And so again, like I said with sine, these are not that hard to see when there's actual numbers in there, because you can evaluate them. But what if that has a variable? And that's kind of where we'll end up at some point. It's like, well, what do we do with variables? Do we have to create like different cases, piecewise functions, that sort of thing? And it turns out that that's exactly what we have to do. Okay, so let's try another. Let me try another example here. How about we reverse the order? So let's take cosine of arc cosine of square root of 3 over 2. Let's make it negative. It doesn't matter. We get the same result. Now, I said this before, that the only thing, when you're taking the trig function of an inverse trig function and they're the same, the argument, it's either going to be one of two things. Either it is the argument or it's undefined. And the only way you can tell it's undefined is if, for some reason, either the inverse function is not defined or the function itself is not defined for some specific angle. But you won't usually have that. The situation will be that the argument is out of the domain of the inverse trig function. In this case, it isn't. So what you would have is cosine of, well, the inverse cosine of root 3 over 2, as we saw right up here, is 5 pi over 6. And then cosine of 5 pi over 6 happens to give us right back the negative root 3 over 2. Very convenient. Now I could probably cook up one where it doesn't have a solution because it's undefined, but I'm just telling you to be super cognizant of those kinds of things. Let's try. I don't need to beat you to death with these. They're all relatively simple, but let's try. Let's try one that maybe illustrates a little bit more carefully what's going on. So cosine of arc cosine of negative 8 over 17. Now this one we don't actually know the what that angle is. I mean, we could beat it into a calculator and probably come up with an approximation, but it doesn't really matter. Just remember, this is a ratio and this is an angle. The arc cosine of some ratio is an angle. And because of the SIGN, we know that it's an angle in quadrant 2. So out here somewhere. And so, we don't necessarily know what this angle is, but we do know that the X value for some point on this terminal ray is negative 8, and that the R value is 17. So when you ask yourself, what is the cosine of this unknown angle? What is the cosine of this unknown angle? Well, it's just X over R, right? It doesn't really matter that you don't know what the value of that angle is. It's just simply X over R. So this will be negative 8 over 17. And it's something you don't even have to calculate anything. It's just, it just kind of pops out like that. So, all right, I'm trying to think if I should push on. I'm going to do, I think I'm just going to come back and do a different session where we talk about tangent. But before I run away, I want to sort of do the same thing that I did with cosecant and do one for secant as well. So section 6.1, page 6. So consider this problem. how about how did I do it with, oh yeah, okay. So consider, how about the secant of, sorry, the inverse secant of the secant of negative pi over 4. Okay, so first off, note that secant of negative pi over 4 is going to be square root of, it's going to be a positive square root of 2. So inverse secant of positive square root of 2. Now, how did I know that? Well, this is an angle in quadrant 4. I mean, we're just simply working with things that we've done before. The exact value for secant in quadrant 4 is positive, and the numerical value is square root of 2. So now the question becomes, what's the inverse secant of square root of 2? Well, you got to remember that secant has a range, inverse secant has a range that is from it's from 0 to pi over 2, or sorry, 0 to pi, except there is no value for pi over 2. So just kind of as an aside, the range on inverse secant is the union of 0 to pi over 2, non-inclusive, together with pi over 2 to pi. Now, does that seem legitimate? Yeah, okay. So we have this whole at pi over 2, because that's actually where cosine is equal to 0. And so since secant is the reciprocal of cosine, you have a problem there. So that being the case, what we're asking is, with this statement, inverse secant is square root of 2, we're asking which angle in either quadrant 1 or quadrant 2 will give you a value where secant is equal to square root of 2. Well, the answer is obviously pi over 4. But notice it's not the same. But these two values, in some sense, remember we were talking about the roots, the principal and the alternate root for cosine. Notice how those are related. They are, in fact, very, very similar. So, but just to kind of hammer home the point that not all of these work, consider this expression. So secant, inverse secant of pi over 2. Now, this one has a problem because secant of pi over 2 is not defined. So this becomes the inverse secant of an undefined ratio. And so this itself is just simply undefined. What about if we reverse the order, and can we make something that causes some problems there? Yes, absolutely. Consider the secant of the inverse secant of 1/2. Now, this is the trick. Normally, as I've said before, it's when you have the trig function of an inverse trig function, it's either that number, it's the argument, or it's undefined. There are really no other options. So the question is, when is it undefined? Well, it's when this angle is undefined. There is no angle for which secant of that angle equals 1/2, right? And so as a result, you can't take the secant of an undefined angle. You once again get just simply undefined. Okay, so you've seen a couple of examples of secant. It's not real useful for us. We usually tend to stick with sine and cosine and tangent, but I just thought I would point out that little extra aspect. And I will see you on the next segment.